I realized that maybe the title was a little bit too ambitious, but so maybe let me explain the plan of what I'm going to do. So since this S-duality for boundary conditions is in the title, I'm going to spend like really very, very short amount of time. I'm going to start with a very short, well, I'm even embarrassed to call it a discussion. On boundary conditions in, maybe I should say supersymmetric boundary conditions in four-dimensional gauge theory. And I'm also going to relate it mathematically to the also to the subject of relative. It's not exactly the same, but there's some connection, which is especially relevant for the purposes of this talk. Relative Langlands duality of which is due to Ben-Sui, Sikelaridis, and Venkatesh. Actually, their long paper was finally posted on the archive today. So that will be a very short discussion. Well, then in number two, so here at least we'll discuss some things we want. And then I'm going to recall something kind of different. Recall two mathematical facts. So I'll do a brief recollection on two things on derived geometric satake. On the one hand, will be kind of two separate facts, although then at some point I'll explain that they're actually related. Causal duality for category O, and then number three is going to be explain number one as a generalization of number two. Actually of derived geometric satake, and then also in this, I also want to discuss this causal duality for category O in this context. So okay, so that's kind of the plan. So somewhere in the middle, we're going to make a break. So maybe the break. So this will be kind of a relatively long subject, and somewhere in the beginning of the discussion of this relatively long subject, we'll make a break. Okay, so let me start. So okay, so what do we start with? So okay, so we're not going to pretend that we're physicists. We're going to do something mathematical and something algebraic rather than analytic. So I'm going to fix a group G. So let's say connected reductive algebraic group over C. And so G check will be the Langlands dual group. And so physics tells the following, has the following kind of narrative that to this group G, to G, one can associate certain unique supersymmetric, well, okay, so what physics calls N=4 supersymmetric gauge theory. So what does N means, I'm not going to discuss. Gauge theory with group G. And so this thing is well, this is kind of amount of supersymmetry you have, and then n equal 4 is sort of the maximum amount of supersymmetry you can have in 4 dimensions, in dimension 4. So in 4 dimensions. So again, you don't really, for the purposes of this talk, you don't need to know what is words mean. So you can, for now, just treat this as a kind of formal symbols. So that there is some kind of structure you can attach to this group, and the structure is kind of the same. Well, there's some equivalence, and this equivalence is called S-duality. S-duality for which is let me call this theory T sub G. This is theory of G. S-duality, let me write it like this. S-duality says that Tg is equivalent to Tg check. And so there's a quantum theory, gauge quantum. Roughly speaking, says this. Now, and okay, so the way we're going to use physics is going to be of the following flavor. That again, so I'm going to treat, as I said, some words from physics as formal symbols. But the point is that some of these formal symbols, I mean, the dictionary is that you can, physicists tell you that you're supposed to be able to produce some of these formal symbols from legitimate mathematical objects. For example, these gauge theories are produced from, you can produce from a group G. Now, when you have such a quantum field theory, it has a notion of boundary conditions, and you can talk about boundary conditions which are compatible with the supersymmetry. So you can consider supersymmetric boundary conditions. And they're kind of the same, but somehow you're going to look at them. But it's kind of the same quantum theory, but it's not the same if you think about it as a quantization of a classical theory. So if you write some fields with Lagrange and so on, somehow this, as classical theories, they're very, very different. But when you quantize them, they become the same. But something kind of crazy happens so somehow if you think about it, I mean, the problem is that somehow it's, it's like it's kind of like religion, that somehow you see that God is not supposed to have any anthropomorphic properties, but we don't have any language to discuss anybody without using some kind of anthropomorphic words. And so therefore somehow when we discuss quantum theories, we usually think we actually do have some kind of mathematical understanding what classical field theory is. But what quantum field theory is, we don't really know. And so we kind of, well, not always, but at least often we're trying to think about quantum theories as some kind of quantization of a classical theory. But that's not really adequate. And for example, so here somehow for S-duality, you really cannot see it on a lot of classical theories at all. But anyhow, so I'm going to be done with this stuff in like 2 minutes. So what I wanted to say is that boundary conditions. So somehow we don't have a full mathematical description of what these things are. In other words, how to construct all boundary conditions. But what there's a work, those kind of relatively old papers of Guyot and Witten, which essentially tell us the following. That Guyot and Witten tell us that one can attach a boundary condition, a supersymmetric boundary condition, to the following data, to a symplectic, let's say algebra. I mean, of course, in the context it's holomorphic, but let me do everything algebraic, or symplectic algebraic variety. Let me call it Y, with a Hamiltonian G action. And so, well, actually, I'm slightly cheating here, and well, it's almost true. So somehow, so you have to, it has to satisfy some anomaly cancellation condition, which I'm going to, which is some kind of Z mod 2 condition. This condition is this condition is automatically satisfied. Let me just say that it's automatically satisfied if y is the cotangent bundle to some x, where x is just a variety with a g actually. And so in this case, you can actually ask when so you can try to compute this. So this is some again, I'm trying to describe what we want. You can try to ask, what the S-dual boundary condition is. Now, for now, we don't really have a language for that, for the following reason, because nobody told you, and generically it's not going to be the case, that I told you that a boundary condition is some kind of mysterious data. You can only attach a boundary condition to some variety with a G action, but certainly not all of them are like this. And if you start with something like this, then it's S-dual. It's not, you're not guaranteed that S-dual is going to be of the same form. So, the way to kind of ask this question slightly more precisely is that can you guarantee by putting some conditions on this y, or maybe x in this cotangent case, can you guarantee that that the S-dual boundary condition is of the same form? And if you can you construct it? And so and this is actually essentially what Gensvisi, Claridis, and Van Kentesh tell you in a different language. They tell you that let me put additional condition. So let's assume that y is t star x. This is actually not necessary, but it will be just easier for me to say it in this case. And assume x is spherical. Which means definition of spherical variety. So it means that x has an open B orbit, where B inside G is a Borel subgroup. So we're going to talk about examples in a moment. Borel subgroup. So then, and actually, there's a way to formulate this condition purely in terms of y. And and this is called, so if you have a symplectic or Poisson variety with an action of G, there's a notion of hyperspherical variety. And for a cotangent bundle to some x, that's equivalent to saying that x is spherical. But there's a way to formulate it purely in terms of the cotangent bundle, which I'm not going to do right now. Let me just make the simple thing. So then the expectation is then the S-dual boundary condition is expected to correspond to some y check with G check action. And so the question that I would like to address is how to actually construct it. Well, we will actually construct it under certain additional assumptions. And so before I tell you what the assumptions are, and then we'll start doing something more systematic, for which I will need to recall this. Let me just make a remark. Then I said that we start with a symplectic variety y with an action of G. Now, the question is, what do I actually mean by this? So usually when I talk about symplectic varieties, you actually want to talk about varieties which are which are smooth. But in general, in this case, even if you start with something smooth, this dual might actually not be smooth. So remarks that this y check is not necessarily smooth. So it will be symplectic in some generalized sense. It will be Poisson and say generically symplectic. It's not necessarily smooth. And sometimes it's not even reduced, even if y is smooth. So, and again, actually, I don't think we'll discuss any non-smooth examples today, but so we'll discuss. So we'll make an additional assumption. So so we'll give a construction for y equal t star x, and also discuss maybe a little bit less rigorously what to do in general, but under additional assumption that given the so when y actually is smooth and affine, and y check in this case will be also affine. And so and this construction, so we're actually trying to give some rigorous mathematical construction of this, but this construction will have this peculiar property that it is actually, again, from physics, it is expected to be symmetric. So in other words, if you start with y, construct y check, then you can also start with y check and construct its dual, and it's supposed to end up with the same y you started with. That will be like highly non-obvious from the construction. It will be absolutely unclear from the construction. The construction will kind of will use them in a very non-symmetric way. So okay, so maybe before we pass to number 2, let me give you some examples of dual varieties, just to see that it's something which, from elementary point of view, it's something pretty crazy. So examples. Example, so very basic example. So example number 1 will be the following. So in this case, I will actually assume that my group is not just my group G. That will be universal example. My gauge group is actually G times G. And X is G, on which G times G acts by left and right translation. So Y is T star G. And in this case, the dual variety Y check is going to be T star G check. That will be example. That will be basic example. So this is actually not very surprising, but then let me give you another example. So what's the and by the way, this thing is spherical because B times B has an the Borel subgroup of G times G is B times B, and it has an open orbit on G when you consider left and right translation. So this is called the open Brouillard cell. But let's consider a much more trivial example in some sense. Let's take any G also. So any G. And Y, which is in this case equal to X, is going to be just a point. What is the dual variety in this case? In this case, it will be not exactly cotangent bundle, but it will be some kind of twisted version of a cotangent bundle. So let me explain what this is. So let me write it, and then I'll explain the notation. I'll write width of T star G check. And that means width means the following thing. Width stands for Whittaker. And that means that it's the following thing. So we take G check. We take U check inside G check. This is a maximal unipotent subgroup. So it's unipotent radical of Borel. And we take chi from U check to the additive group generic character, generic homomorphism. And then we consider the corresponding Hamiltonian reduction. So Whittaker of T star G check, or as a matter of fact, any variety with the Hamiltonian action. So we have this, we have the moment map from T star G check, to the dual space to the Lie algebra, which you can, if you you can just identify this tangent bundle with G checks times the dual space of the Lie algebra, and it will be just a projection. And then you can further project it to so this is the moment map for G, and also you can construct the moment map for any subgroup. So if you can see the moment map for the group U, then you can just further project it to U check star. And this thing is just the corresponding Hamiltonian reduction. Take mu U of inverse of the point 1 not of 1, of chi. So chi can be, it's a homomorphism like this, but you can also view it's the same as, this data is the same as to give the corresponding homomorphism of Lie algebras. So it's chi can be thought of as an element in the dual space to this Lie algebra, and quotient by check. So this is some Hamiltonian reduction of this character. And this thing, it's also, in fact, isomorphic, but it's less obvious how to construct symplectic structure as to G check times. It's an exercise. It's isomorphic to G check times the adjoint quotient of the dual space of the algebra. So that's example. That's another example. And so maybe example number 3, which we'll discuss a little bit, is the following. So let G be the following group, GLN times GLN. And let's consider the following variety. Let's consider variety X, and then Y will be its cotangent bundle, which is just matrices of size n times n. So then GLN times GLN, X here obviously natural way in some obvious way. And so Y is T star X. So the question is, who is Y check? And well, it would take me actually some time to describe it for arbitrary n and m. Let me do it in an example where it's the easiest. Let me do it in an example when m is equal to, say, n minus 1. Let me explain it in this case, just to show you that the answer is kind of not something you could guess from just doing nothing. So the answer is the following. It's again going to be of cotangent type. In this case, Y check is going to be the cotangent bundle to just the group GLN. So note that the dual group here is also GLN times GLN, because GLN is self-dual. And so this thing, so on GLN, you have a natural action of, well, the group GLN X here on the left. And of course, it also acts on the right, but on the right, we can just don't use the action of the full GLN, we only use the action of GLN minus 1, which sits inside GLN in some standard way. And this thing is still spherical. It's not completely obvious, but somehow it's not a difficult exercise in linear algebra to show that if you can see the Borel subgroup here and Borel subgroup here, then together they have an open orbit inside GLN. And it turns out that the dual variety is like this. And maybe another flavor of this, if I take m equal to n, then the dual variety is going to be the following thing. It's again cotangent bundle. And in this case, it's cotangent bundle to GLN times c to the n. And here there's a natural action of GLN times GLN. So essentially this action is like this. One copy acts just here on the left, and the other copy acts here on the right, and also acts on c to the n in a standard way.
Is the dual always cotangent?
No. In fact, in this case, it's not.
For n.
No. For example, if m is equal to 0, that's a special case. That's a special case of that. So and so in general, it's going to be some kind of mixture of this and some Whittaker stuff. So, but again, it's not so difficult to describe, but just I don't see any point in doing this right. Okay, so So for now, you can think about this as some series of crazy examples. So the goal will be to set up some formalism so that all of these examples will be special cases of that form. And okay, any more questions? Okay, now let me pass to let's forget about this stuff for some time. So I need to recall some something about derived geometric satake. Number 2. So, well, I'm going to recall it some particular way. So, okay, so what is the setup? The setup, well, the standard setup was the following. So we're going to introduce the field K, which is the field of Laurent power series in some form of variable T. Inside we have the O, which is its ring of integers. And then, of course, the main thing we're going to play with is the affine Grassmannian of G, which is G of, well, said theoretically, it's this, which is some kind of infinite dimensional object, but somehow it's known that this has a canonical, this set actually is the set of C points of some canonical in scheme. So this can be written as inductive limit of, well, usual fine dimensional projective schemes, and inductive limit with respect to closed embeddings. And so, and what the schemes about more or less are, especially when G is semi-simple, is that we can see the G of O, or so G of O still acts here on the left, and its orbits are finite dimensional. So it's has finite dimensional orbits, which are in fact in one-to-one correspondence with lambda, which are dominant co-weights of G. There are discrete number of those, and that will be actually so note that that's the same as to say that in particular we say that G of O times G of O has discretely many orbits on G of K, and later on there will be some generalization of this fact. So this in fact is turns out to be, this condition turns out to be equivalent to the condition that G is a spherical variety with respect to G times G. But this we'll discuss later. And so then there is this geometric satake. So there are kind of two statements. Well, there will be kind of three different statements. So first of all, there's a abelian geometric satake. So abelian abelian geometric satake says the following thing. Abelian geometric satake says that we can see it's some equivalence of monoidal category. So we can see the perverse sheaves on the affine Grassmannian, which are G of O equivariant. So this is actually a perfectly legitimate mathematical object because these orbits are fine dimensional. The closures are fine dimensional. So in fact, we're doing some kind of fine dimensional algebraic geometry here. And so this has a natural monoidal structure, in fact, symmetric monoidal structure. So this is kind of always, you can think about this thing, it's the same as sheaves on G of K, which are equivalent with respect to G of O and G of O, G of O times G of O. And so in such a situation, you always can construct some kind of monoidal structure here, which is given by some kind of convolution. So think about just a baby example of how finite group and the subgroup, then functions on the group which are say left and right invariant with respect to the subgroup, they form a subalgebra in the group algebra, and that's kind of essentially the same type of thing. So the fact that the abelian category of perverse sheaves has monoidal is preserved by this monoidal structure is actually not obvious, but in this case it's true. And it says that this category is equivalent to the category of representations of the Lagrange dual group. And in some sense, that's the right definition of what Lagrange dual group is. So that's the kind of first approximation to what we want. But in fact, we want not this. We want I want to do it not for the abelian category, but for the derived category. So let's do the derived category of G of O equivariant. And so I want to formulate the statement, and then I want to maybe do a couple of examples here. So, okay, so here, there's some kind of question of what exactly you mean by this equivalent derived category. So, for example, the way I'm going to formulate right now, this is going to be due to Rukovnikov and Finkelberg, but then maybe I'll mention some slightly finer statement due to Arinkin and Gatesbury. So here, let me put B. So it means bounded derived category. So what I mean by bounds, first of all, this is actually bounded derived category, and also such that every particular cohomology is an object of with fine dimensional support. So somehow then this thing turns out to be equivalent to the following thing. Let me write it and then explain the notation. We take the following okay, let me write it and then I'll. Okay, so what does this mean? So probably need more space. So first of all, what is this, guys? So we just treat this we just treat this as we treat this Lie algebra just as a vector space, and now forms the following DG algebra. We just first of all, it's going to be DG algebra with zero differential, and by the way, there's some if I'm writing this carefully, I need to maybe write here finitely FG, which will stand for finitely generated. So this is a DG algebra with zero differential. And what is this DG algebra? So it's really the symmetric algebra of our Lie algebra, except that we put the generators in degree +2. So shift by -2 means that we put generators in degree +2. And then, so in other words, we take the kind of, well, on a symmetric algebra of G check, but we introduce some homological grading on that. And so the homological grading is the standard grading of the symmetric algebra multiplied by 2. That's essentially what this thing means. So it's a DG algebra in degrees greater or equal than 0. In fact, with zero differential. Now, modules over there. So if we have any DG algebra, we can consider the category of modules. In fact, FG means we consider finitely generated modules, and we consider the derived category. So for a DG algebra, you can define a derived category of DG modules. which are kind of defined similar to how I usually define derived categories. If you have any experience with that, so somehow you can see the differential graded modules, and then you consider the category of differential graded modules, and then basically invert the quasi-isomorphism. So then you can see the so this thing mod means that derived category of DG modules. Note that for the algebra has zero differential, but DG modules, of course, are not required to have find zero differential. Oh, sorry, the algebra has zero differential, but the modules are not required to have zero differential. And then the thing is, then G check means so, well, finitely generated just means finitely generated. And when I put here this invariance vector G check, so this symbol means G check equivariant. And that means that we can see the modules over this thing on which there's an additional action of the group G check, which is compatible with its adjoint action on the our algebra. Now, note that just a remark is that if we ignore the homological grading, then we're talking about the following geometrically. We're talking about G check equivariant, coherent sheaves on G check star. So what does mean? So if we didn't have this homological grading here, we would be just talking about modules over the symmetric algebra, which is the same as finitely generated modules over the symmetric algebra, which is the same as coherent sheaves on the dual vector space, and which are equivariant with respect to the group. And this is some kind of DG modification of that. So that's what this at least some version of this geometric satake says. Now, a remark, maybe let me put it here, is that this is this Rankin-Gainsbury thing, so which I want to mention just for the sake of completeness, but I don't want to discuss it for now. Remark is that if you remove this boundedness condition, then you might think that you just need to remove finitely generated here, but that's actually not the case. So, and this is because it turns out that, well, in this situation, this full derived category is actually not the incompletion of this bounded derived category. In other words, or another way to say this is that not all objects in this bounded derived category are compact objects in this full derived category. So actually, if you consider the full derived category, this is equivalent. This turns out to be equivalent to something well, similar. Mod G check, but I also put nilp here, and nilp means we can see the module. So again, let's ignore the homological grading. It's so then we're talking about, as I said, we're talking about coherent, maybe this now quasi-coherent sheaves on G check star, which are equivariant with respect to the group. And nilp means that they kind of set theoretically supported on the nilpotent column. I'll just write it once for the sake of completeness, and then I'm not going to mention it again in this talk on the nilpotent column. So this is our Rankin-Gainsbury, and again, I'm not going to worry about such fine things and for the purposes of this talk, but I want to say that if you want to remove this boundedness condition, then somehow you have to be careful about what the right statement is. But but again, for people who know what these words mean, let me just say it. For people who don't, we can just ignore this. Okay, so this is what derived geometric satake is. So now, by the way, it makes sense to discuss how one is compatible with two, because of course, just on the level of left-hand side, perverse sheaves are just some special objects of the derived category. So you can embed this category into this category. It's not actually a full embedding because somehow, well, you have more. So x, you have equivariant x between them, between the perverse sheaves, which do not necessarily sit in degree 0. But in any case, somehow you have this. At least you have this functor. And so what is this functor here? So this functor here is the following thing. You take v, which is in rep g check, and then you what you want to do with it, you want to construct a module over this thing. So how to construct a module together with g check action? And you take the following very simple construction. You take this algebra itself, multiply by v, and this obviously has a module structure, but also it has a g check action. And so the module structure just comes from the first factor. But the g check action is the diagonal action, is the action on the I mean, g check acts on this on the first factor and on the second factor, so it acts on the tensor product. So in other words, the objects of the abelian category, they kind of correspond to free modules. To free modules with generators in degree 0. So that's this is derived geometric. So I also want to discuss quantum derived geometric satake. But before we do that, let me maybe do one more example. So here, so for example, so let me discuss some examples of which things correspond to which things. Right. So I already described it for the objects of the abelian category. So in particular, kind of here is a very special example of an object in abelian category. So inside of this Grassmannian, it's g of k mod g of o. So we have the point 1 here. Let me put and this thing is obviously invariant on the g of o. So this thing is a closed. This thing by itself is a closed g of o orbit. And this corresponds, so therefore you can consider the constant sheaf let me put C sub E. This is the kind of, constant sheaf sitting at this point, or skyscraper sheaf at this point. And E. And it corresponds to, it is a special object it is a perverse geophoric covariant sheaf. As a perverse geophoric covariant sheaf, it corresponds to trivial representation under abelian equivalence. And therefore, by what's written over there, this thing corresponds to just our algebra itself as under derived. In one is abelian, two no. So one is abelian because it's perverse is an abelian category, and this corresponds to the abelian category of representation. Yeah. So 2 is the derived equivalence. And so in two, I kind of manifestly on the left-hand side, I say the derived. This is equivariant derived category. Equivariant derived category, it's what I should remember is about it is that it's typically it's not the same as the derived category of the any abelian category. And it turns out to be equivalent to this category of DG models over some DG algebra. So the algebra itself here corresponds to this skyscraper at one point. Now let me consider one more example. Let me consider let me consider slightly illegitimate example. So it will not be an object of the bounded derived category, but it will be an object at some kind of inductive limit of such things. So I want to consider essentially I want to consider the constant sheaf. The constant sheaf is actually not an inductive limit of such thing, but a projective limit, and that's not. I want to actually avoid projective limits. So instead of considering the constant sheaf, I want to consider the dualizing sheaf. Let's consider the dualizing sheaf of the affine Grassmannian. So first of all, how do we think about this? The way we think about this is that we write the affine Grassmannian, first of all, as an inductive limit of some finite-dimensional varieties. Finite-dimensional variety, well, let me actually write them. So I'll write them like this. So here, what is this GR lambda? This is just the orbit of GFO corresponding to lambda. Then we take its closure, and this is finite-dimensional projective variety. So then I can put honestly a dualizing sheaf on each of those. And then if I have a closed, and then when lambda grows, this thing, well, I get, if I increase lambda, I get a closed embedding from this thing for smaller lambda, this thing for larger lambda. And if I have a closed embedding of two algebraic varieties, then I get a map forward between their dualizing sheaves. So I consider limit like this with respect to lambda, and that's what this thing is. So it's formally speaking, it's going to be an object of some int completed category. And so, but again, let me not worry about formal definitions. Now the question is, where does this go under satake? And just to play with these examples, this actually goes to something which you have already met. This thing, well, let me write it again. I'll give you an answer, first of all, sort of ignoring again the homological grading. So this thing is our familiar Whittaker reduction of T star G check. Well, or rather, sorry, I should take functions on that. So this should be struct. Okay, so first of all, in this field of mathematics, there's a standard problem that the letter O always denotes two different things. It's the ring of integers of our K, and also the structure sheaf of something. And so if you're actually writing something in TeX, you can relatively easily fight for this problem because you can use different fonts. On the blackboard, it's more difficult. Let me use maybe O like this for the structure sheaf. So it's so what does it actually mean? So it means the following thing. So if I take this variety, then whatever it is, it actually I claim that it actually maps canonically to G check star. It's an affine variety, first of all, and it maps canonically to G check star. And why does it map to G check star? Because this G check itself, or same as T star G check, it originally had two G check actions on the left and on the right. One of them we used to perform this Whittaker reduction, but that is still there, and it is still Hamiltonian here. So we still have the moment map here. So it's still, so this thing still has an action of Hamiltonian action of G check on one side. And so, and we still have the moment map. And you can actually write it down explicitly what this map is. And you can write down explicitly what this variety is. You can write down explicitly what this map is. So it's not difficult to do. But let me just say that this thing is kind of a priori there. And it's a map of fine varieties. So therefore, if we take the structure sheaf of this variety, we can think about it as an algebra over as a quasi-coherent sheaf of algebras on this G check star. So this is what I mean by that. And so well, again, so here I have ignored the homological grading, but it's easy to actually restore this because the homological grading here just corresponds to it. Just it's just we just shift the generators by 2. So in other words, what I want to say is that you can think about this in the following way. You can so this thing it's you can think about it as just an algebra over. So let me write this. So this. This O of wheat of T star G check. This is an algebra over seam G check. But in fact, it's a graded algebra. And it's a graded algebra with respect to the natural grading here. And this comes from the following, that somehow here, well, what do we need to actually to construct a grading on an algebral function somewhere? We need the C star action on that something. So for example, here, the C star action is just the standard dilation action on G check star, or rather it's kind of double cover because we want to put all the generators in degree +2 rather than +1. I claim that here we also have a similar action because originally we had also a C star action on this T star G check, which was just by sort of dilations of the cotangent fibers. And this action sort of commutes with everything we do here. So when we perform this Whittaker reduction, that's still there. So this thing still has a natural C star action. And this C star action is compatible with this moment map because it commutes with our G check action. And so that's what we use to construct this grading. So have a natural star action on sorry, with okay. Soon I'm going to make maybe a break, maybe sooner than I expected. Maybe let me talk for about 5 minutes. Okay, so so maybe I'll skip this causal-duality discussion because maybe I'll come back to it in the end. But so okay, so this is this and let me also maybe skip for now the quantum satake. So maybe let me just say what the quantum geometric satake is about. This is relevant, but I'll maybe prefer to skip it for now. So quantum derived satake describes the following. It's the derived category of the affine Grassmannian. Well, not just with respect to G of O, but you have an additional C star action here. And so this C star is what's called loop rotation. And loop rotation means the following. So remember that the affine Grassmannian was G of K mod G of O. And just on K itself, and on O, we have a natural action of C star, which just kind of rotates our generated T. So this thing was C of T. So here we some element lambda in C star. Well, not lambda is a good, it's not A, let's say it's C star. It maps T to A times T. And so it induces an action on K and on O, and therefore induces an action of G of K and on G of O, and therefore induces an action of Grassmannian. And so we can, in addition, consider things equivalent with respect to the C star. And if we do that, it turns out that, so here again, this thing was a monoidal category. In fact, it was a symmetric monoidal category. So we actually, if we do it like this thing will still be a monoidal category, but it will not be a symmetric monoidal category anymore. And in fact, somehow the phenomenon we'll see is that the symmetric algebra will get quantized to the universal Velikan algebra. But let me skip the exact formulation for now. So let me just say that, okay, let me just say what that quantum, well, this is supposed to be part 3 here, but let me maybe come back to it a little later. So maybe let me formulate then some kind of some kind of property of the construction that we want. So now kind of back to S-duality, which is also the same as relative Langlands duality in the language of, well, relative Langlands duality is a kind of special case of S-duality in this under this assumption that something is spherical. So if y is equal to T star x and x is smooth affine, and spherical, then the idea is that, well, smooth affine or, well, spherical, let me put it in parentheses, because the constructions, in fact, will not use the sphericity assumption, but some kind of, we'll get something interesting, I think, only under the assumption it's spherical. Then the idea is that in that case, we're going to construct some y check with g check action, also affine. And so we'll have the algebra of functions on y check. So y check will be spec of this thing. Now, because this thing will be symplectic or Poisson, and this will be Hamiltonian action, the idea is that there will be a moment map to G check star. This moment map will tell us that this algebra of y check will be an algebra over this thing. Now, in addition, there will be some C star action. By construction, there will be some canonical C star action on this y check, which is going to be compatible with this, which actually kind of dilates the symplectic form appropriately, and which implies that it's compatible with natural C star action under the moment map. It's compatible with natural C star action here. So in fact, this thing can be made into a graded algebra, and then we can again, if it's a graded algebra, we can again think about it as a DG algebra with zero differential. So and notation for this is this. So Bensvisa Claes call this procedure shearing. So that means that we have a graded algebra and we make this grading into homological grading. And we put again all the generators in even. We put all the. I mean, we can multiply everything by 2, so we put everything in even degrees. And so and then the claim will be that so there will be construction, and more or less by construction, the following thing will be true, that there will be some analog of derived geometric satake, that derived category of geophoric variant sheaves on x of k, that will be equivalent to yes, one more thing. Yes, and so this yes, I said everything I need. So this thing will be the same as O Y check sheared modules. Yeah, G check with regard. And so this will be essentially by construction. So originally, Bensvisa Claes and Venkat they actually wanted to. I mean, they had a lot of examples, and they conjectured some kind of equivalence like this. But then somehow, if you actually find the general construction of dual variety, then it turns out that this is essentially built into the construction. Let me just say that an example is that if you take again if you make your group to be G times G, and you take X to be G, then then here you have to consider G of O times G of O equivariant sheaves on G of K, and that's strictly the same if you kill one G of O by just modding out G of K by G of O. That's the same as G of O equivariant sheaves on Affine-Grassmannian. So in this case, we're really dealing with the geometric satake example, and I told you that in this case, Y check is supposed to be the cotangent bundle to G check. Now, well, again, let me ignore this shearing business. It's really not a big deal. But let me just say what does it mean to consider modules. So we consider something, well, considering modules geometrically means that we consider quasi-coherent sheaves on the corresponding variety, right? So what does it mean to consider quasi-coherent sheaves on T star G check? And again, let me ignore the homological grading. It's not really important, but I want to consider G check times G check equivariant. So how does T star G check look like? So if we use the action, say right action, then we can identify it with the group times the dual space of the Lie algebra. And so if we want to kill this, if we want to consider things equivariant with respect to right action, then we can kill the group and just be left with the Lie algebra itself. So I claim that this is the same as quasi-co of the following thing, of just dual space to the Lie algebra. And now equivariant again, just with respect to just only one copy of G check. And how does this one copy of G check act here? Well, there's only one action, which is the adjoint action. So this is an X. This is like a trivial exercise. So what I want to explain is that what I want to say here is that in this example, so we're going to present some construction after the break, which is going to have this property more or less by construction, and such that the derived geometric satake will be a special case of that. The drawback of this abstract construction I'm going to explain will be that it will actually, and yes, the drawback of the construction will be that if you start with some particular example, it will be usually not easy to actually compute this dual. If you want to compute this dual in some explicit terms, not by means of some abstract nonsense construction, then it might actually be difficult. But so I will try to let's make a break. I'll make a short break, and after the break, I will tell you what the construction is, and we'll tell you some examples. Well, where it is known that it actually gives some explicit answer. Okay.
Back.
Okay. We can discuss some questions in the meantime.
Ну, это вот, пусть у меня, например, там, теория Сатаки, вот, несколько там, скажем, кольцевой объект. Да, могу построить объект на пространстве равно. Хорошо? Ну, как бы, получается, у меня как бы давай, да, я завтра буду. Да, давай завтра. Завтра много чего происходит. Но нет, у меня за там нет. Хорошо.
Do you know what this association of these varieties to boundary conditions? Are they the boundary conditions?
They are some boundary conditions.
I see. There's a choice of boundary conditions for.
Well, I mean, any theory, there's a choice of boundary conditions. So, there's some space of choices. You could name some of them. Some of them are named in this way.
How do mathematicians?
So now let's go back to some kind of slightly more elementary discussion. So what do we want to construct again? So what are we after? What we're after is the following thing. So okay, so we start with some g acting on some x, and then we have y, which is t star x, and I'll talk maybe, if I have time in the end, what to do if it's not if it's not cotangent. Then what we want is want to somehow construct some kind of y check with an action of g check. And now, for now, everything is fine. So somehow this y check is supposed to be a spec of some algebra. And now, and this is supposed to be more or less symplectic, at least Poisson, and generically symplectic. And it's supposed to be Hamiltonian action. So we're supposed to have a moment map into here. And so it means that this algebra means that this O of y check, this is an algebra over sim g check. And this is an algebra of sim g check endowed with a compatible action of g check. Now, again, if we kind of ignore the homological grading, this sort of looks like an object which appears on the right-hand side of our derived geometric satake. Or moreover, it's a ring object in this derived geometric satake category because it's an algebra. Let's ignore the algebra structure for a second. Then it will be just a module over the sim g check endowed with the action of the group g check, compatible action of the group g check. So if we actually restore the let me write it here. So if this all y, if y check, let's say, has also a C-star action with respect to which the symplectic form has degree 2, then we can perform this shearing construction. Then this OY check sheared is literally an object on the right-hand side of derived geometric satake. But it's not any object. It has an algebra structure. So in fact, it's a ring object. It's a ring object. Moreover, so this derived geometric satake category, this is a monoidal category. And so what we need, and so actually a more precise statement is the following, that any ring, a ring object, let's say any commutative ring object, so of course, honestly, I have to do all of this in some DG level, but let me, again, not do this for the purposes of this talk. In this category gives rise to the above structure. And by above structure, I mean what's written here in the fine variety. Well, except that maybe it's what is not clear is where the symplectic Poisson structure is coming from. Up to Poisson structure. And so for this, I actually need this quantum geometric satake, but so I don't have probably time to explain this, but let me say that the Poisson structure will be there if any commutative ring object, let me call it A, if A deforms to, well, deforms means that we're given a canonical deformation of A to a ring object in this quantum derived geometric satake. So this I don't have time to explain, but the idea is that if we can deform it to here, then this A then the image of this and the geometric satake gets endowed with the canonical non-commutative deformation. So in particular, A gets endowed with the Poisson structure. So let me ignore this point for now. But let me just say that this Poisson structure on this Y check can also be constructed canonically from these considerations. Well, if we use this quantum derived geometric satake. But again, so the point of what I'm trying to say here is that in order to construct this some kind of structure we need on the right-hand side, we need some kind of nice ring object in derived geometric satake.
Right, but this Poisson structure, is this in addition to the symplectic structure on both sides? Or
No. Poisson structure, again, no, okay, the logic is different. So I'm saying that forget about everything, just forget about X, Y, whatever. Suppose that I give you, a ring object in this category. Then apply, well, okay, let me also ignore some DG problems. Let me take common, just apply this derived geometric satake to it. So you get the DG module are, well, over seam G check shifted by 2. In fact, it's not a not just a DG model, it's a DG algebra over that thing. Let's take its cohomology for simplicity, or all nice cases will be formal. Then we'll get an honest algebra over the symmetric algebra of G check. So its spec will be some scheme. And this scheme will be, well, it will be endowed with a canonical map like this, and will be endowed with a canonical action of G check. And actually, the additional thing we need a Poisson structure on the scheme, so that this is not just an abstract map, but such that this is a moment map with respect to that Poisson structure and this canonical action of G check. And I claim that it will also be automatically there if, but for this ring object has to be not a ring object just in this category, but in fact it has to be upgraded to a ring object in this category. So in other words, okay, maybe a better way to say this is if we start with a ring object in this category, then it will give us all the structures that we want. So yeah, maybe that's the better way to say this. Well, a ring object such that if we ignore the equivariance with respect to the slope rotation, then it's a commutative ring object. So conclusion, a ring object, a commutative ring object in DG of O of the Grassmannian, which is also deformed to the note that in this category, it makes no sense to say that some ring object is commutative, because this category is just monoidal, but it's not a symmetric monoidal category. Commutative ring object is only makes sense in the symmetric monoidal category, and of which this is symmetric monoidal, this is not symmetric monoidal, which gives rise to Y check as we will. Again, if we want to be really careful, that this is also modular. This is ignoring some DG problems, which are usually not there. So by ignoring DG problems, I mean we actually construct some DG algebra, and then we actually pass the cohomology of this DG algebra, which is not a very nice procedure, unless the algebra is formal. But in fact, usually it is formal. So usually it is a harmless procedure. But this is something that it's better to address, which are usually not present. Okay. So now let me finally give you the construction. So again, I will, because of lack of time, I will give you the construction only in this cotangent case. In this case, it is actually so I will discuss the construction when Y is T star X, X is smooth and defined. So in the non-affine case, I don't know what to do, how to do anything at all. So in this particular case, this is actually appears, among other things, in this Vinsvisa, Clarice, and Venkatesh. Now, if so, smoothness should be removable, but it's a serious issue. What to do when this thing is not smooth, or more general, or actually, on the other hand, if Y is smooth affine but not necessarily of cotangent type, but not of type T star X, then essentially there's it is explained. This my if you look at my paper with many authors, this Gorbier, Tilion, Finkelberg, Raskin, and so this is right. Finkelberg. Raskin and Travkin. So it kind of addresses essentially this issue. It only addresses this issue in case when Y is a linear representation of G, but it's kind of explained there what, well, it's the same type of problem. So again, let me put just in parentheses. I'm not going to discuss this for now, but so I'll only tell you what to do in this case, in the cotangent case. And so how to produce this ring object. So I will give you some kind of maybe I'll. So what time is it? There was a clock here somewhere.
It's 3:36.
3:36. Okay. So let me give it maybe two constructions of this. Two equivalent constructions. So construction one is, which is more geometric and less categorical. Construction one is the following. Let's consider. So, well, we have the affine Grassmannian. I'm going to construct some space R sub x, which leaves over that. By space will actually mean in scheme. And so in fact, well, it's just geofour equivariant. In fact, it will be even easier for me to take the quotient by geofour as a stack. But or well, let me just say it like this. So I'm going to construct some canonical in scheme here, and then my ring object, my A, which depends on X, will be the pi lower star of the dualizing sheaf of this Rx. So, and let me tell you what Rx is. Rx, so it's easy. It's the easiest way to think about it is in terms of modular description. So how do you think about the affine Grassmannian? So one way to think about the affine Grassmannian is that it's the modular space of the following data. So let me put F, which is a G bundle on the formal disk, on spec O, which is the formal disk, plus a trivialization on spec K, which is the formal puncture disk. So that's the claim is that the affine Grassmannian is canonically like this. So let me, in this terms, say what our X is. Well, around what is X? Well, X was a variety with a G action. So if I have a variety with, if I have a principal, so an F, so G bundle means principal, G bundle, of course. So so given trivialization, let me call it kappa. So if I have this F, which is a principal G bundle on something, on spec O, we can form F sub X, which is a corresponding X bundle. So whenever we have a space in which the group X, and if we have a principal G, which the group GX, and we have a principal G bundle, we can consider the corresponding associate X bundle. And so this Rx consists of the following data. It's F kappa phi, where this F and kappa is before, and phi is a section of Fx, but such that it is also such that it has kind of no singularity with respect to kappa. Well, if you write it, and then maybe I'll explain slightly differently. It has no singularity with respect to kappa. And one way to think about this is the following. So what is kappa? Kappa is an isomorphism between f restricted to spec k and f naught restricted to spec k, where f naught means trivial bundle. So this means trivial. And so here in particular, if I take this fx, if I restrict it to spec k, it's well, here it's isomorphic to well, let's say spec k times x. And so if I have a section of phi, if I have a section of this fx, in particular, I get a section on the formal puncture disk. And the formal puncture disk, I get a section of a trivial bundle. And I want the section of a trivial bundle to be extendable to the full disk node. So it means that so phi, that means that phi corresponds to some phi naught, which is a section of f naught x on, and here I want to write spec O. So kind of for free, if we have this section, we get if I have this phi, we get a section on of the trivial bundle on spec k, but I want it to be actually to come from a section on spec O. That's what it means for us to have no singularity here. It's easy to write it set theoretically, but I think it's more instructive to write it like this. And so, well, things are slightly infinite dimensional here, so I have to be a little bit careful by what you mean by dualizing sheaf and so on, but this is not difficult to say. And so this is very much, so in the case when X is a vector space, this is done carefully in our paper with Finkelberg and Nakajima. And so the lemma is that if I take this pi star of the dualizing sheaf of Rx, this has this thing is a commutative ring object in the derived geometric satake category. And moreover, because everything is compatible with loop rotation, so it can also do this in the kind of quantized category, because this loop rotation acts with everything, and it commutes with everything and so on. So this is our ring object. Now let me well, I'll give you maybe a slightly different construction of it in a second, but before that, let's consider an example. Example is, suppose that x is equal to a point. Then what is this Rx? Rx is going to be the affine Grassmannian itself. And so who is our ring object? Ring object is going to be just, by definition, is the dualizing sheaf of the affine Grassmannian. And I told you that if we now apply satake, what we get is the structure sheaf of this Whittaker reduction of T star G check. Well, shared if you want. And that's precisely corresponds to what I told you even earlier, that in this case, so if we take y equal to x equal to point, then I told you that y check is this Whittaker reduction of T star G check. This is what you see here. So in other words, in this case, just to if we believe that this is the right construction, right kind of well, in this kind of relatively general context, then to prove that the dual to a point is this, what you need is to compute the image of this ring object on the derived geometric satake. And this is actually, this statement actually is in the original paper of Bezrukavnikov and Filkerberg, that it's equal to this. So it's so this we have now. I only told you what to do in the cotangent case, and so this thing by itself, it's not really a cotangent bundle, but it's almost a cotangent bundle. It's what's called a twisted cotangent bundle. So it's a Hamiltonian reduction of the cotangent bundle. If we would just really taking Hamiltonian reduction with respect to the important group and trivial character, then this thing would be just cotangent bundle to G check mod U check. So in this case, it's not. It's some kind of since we're taking Hamiltonian reduction with respect to non-trivial character, it's not literally a cotangent bundle, but it's actually easy. Let me not do this. It's easy to adapt this construction to their situation. And I can leave you as an exercise. Well, exercise. Show that the converse is true. So show that if we take this Whittaker of T star G and then take its dual, then we get a point. Well, part of the exercise is sorry, not T star G, but this Whittaker T star G. Check. Let me put it like this. Part of this exercise is to say carefully what this means, because I said that this thing is not literally cotangent bundle, but it's very close to cotangent bundle. So we can actually. So in other words, you can define also in this case this corresponding ring object in the satake category, and then you want to compute its image under the satake, and this image under the satake turns out to be something like literally trivial. It turns out to be just one-dimensional space with trivial G-check action, trivial algebra structure over sim G-check. Okay, what is less trivial but done is so known that what I told you also in the beginning, that if you start with X, which is this matrices of size n times m, and take G to be GLN cross GLM, then Y check, so Y is star X, then Y check can be computed explicitly. Again, I will be just too many notations maybe for now to give you what this answer, to tell you what the answer is explicitly. So let me just tell you that, for example, if m is equal as before, if m is equal to n minus 1, then this Y check is just T star of GLM. And if m is equal to n, then Y check is T star of GLM times C to the n. In fact, in this case, you can prove that it works sort of both ways. And it was originally in my paper with Finkelberg, Ginsburg. and Trofkin, and then the general. This is maybe these two cases were in this paper, and the general case was in the paper of Trofkin and Young. And of course, I should say that the fact that it should be like this, that was actually that kind of appears also in this Ben-Svisa, Clarice, and Venkatesh, but also it was also appeared in physics literature. It was also well, there's a general answer for arbitrary M and N, which I'm not going to tell you, but but let me write. It was a conjecture of Gayotto. So Gayotto, from kind of physics considerations, was able to produce the answer. So let me maybe, before I finish, let me give you a slightly different construction of this thing. And I told you that there's some equivalence of categories which is built into this construction. So let me reformulate this construction in such a way that this equivalence of categories will be more or less apparent there, or at least a function in one direction will be apparent there. So let me, that will be the last thing I'm going to say. So let me discuss some abstract nonsense. Abstract nonsense is the following. Suppose we have A, which is some algebraic group, and or in the algebraic group. So we're going to apply it later to A being equal to G of K, and B inside A is this is a closed subgroup, and we're going to later apply it to B equal to G of O. But I want to sort of do it in general, and C will be some category. Well, if you work carefully, it's supposed to be DG category, but let me just say category with what's called let me not go into details, but for people who have heard those words, with a strong A action. Then we can perform the following construction. Yes, and let's suppose we also have another thing. Let's suppose we have F, which is an object of C, which is B equivariant. Then we can, to that thing, we can associate something like endomorphisms of in endomorphisms of F, which is going to be a ring object in the derived category. Well, in this case, well, in this generality, we need to work with D modules, on A times over B or over B, quotient by B on both sides. And so what is this object is, how to construct this object? So it's, let me say that its Schrieg stock at the point A in A is the following. It's equal to hom from F to F shifted by A. So we have A action on our category, so we can apply it to our object. We can apply an element of A to our object and then take home. So we get something which depends on A. And the fact that it's a strong action precisely means that it's well, first of all, it really lives on this double quotient, because this F was B equivariant. So therefore, it's more or less obvious. First of all, if we multiply A by something in B on the left, then or say on the right, then this F A does not change by definition. But also, if we change by something on the left, then this hom also doesn't change, because we can sort of pull this on the other side. And so it's very easy to see that this really lives on this double quotient. But also, it's a D model. In fact, it's a D model kind of hidden in this notion of strong action. So this kind of object like this, and moreover, we have a functor from well, we have the following two functors. In fact, we have functor from C to let me write it like this: D mod A mod B ring object. Let me call it E, just to distinguish it from A. E. And so this means that these are D modules here, which are also modules with respect to this ring object. And also we have a functor, okay, a variant of this functor is that if we take B equivariant objects on C, we can use the same functor, well, similar construction of functor, and we take G mod also E on A mod B mod B. And what this functor is, again, so how does this functor work? Well, again, we start with any G in C. And what we do is we send it, then the, well, let me call this functor F. Then we want to construct this F of G. It's Schrieg stock at some A is equal to home from F to G shifted by A. That's kind of, well, I have to say these things more carefully to actually construct a D module here, a D module here, but that's really not difficult. Okay, so then I'm going to then really now assume that A is G of K. And yes, and so we have this functor, and moreover, this functor kind of well, okay, so let me, I wanted to say something, but I'll say it in this example. So I take A equal to G of K, B equal to G of O, and C, I want to take the category of D modules on X of K. Well, again, X of K is a slightly infinite dimensional object, so I have to be careful what you mean by this. But when X is smooth and affine, this is okay. You can define this category without any without much trouble. And then yes, and so who is this object F? And F is the structure sheaf of X of O. Then we imply this construction, and the claim is that, and then kind of lemma, which is very easy, is that if you follow the construction that this object A sub X, this ring object A sub X that I defined, this is exactly this E I was talking about above. And in particular, so that's the last thing I'm going to say here. In particular, we get a functor D mod X of K G of O. So here all categories are derived into this D. Well, let me write it now. G of like this, G of K mod G of O mod G of O. And here I write this A sub X. So it means that object, this kind of module object over this in this derived satake category, which we can translate then into kind of elementary language by using the statement of derived satake. And so a priori, this is just a functor, but the claim is that this is, again, easy claim is that if X is spherical, then relatively easy claim, then this functor is an equivalence. This is because in this general construction, this function, we know that at least on some subcategory, this functor is fully faithful. And namely, if we consider things which are obtained from this f by the action of some, so we can act on f by any object in our derived satake category. And if we can see the category generated by those, then on this category, this functor is fully faithful more or less by construction. And it turns out that spherical condition is actually equivalent to saying that this whole category is generated by under satake action by the structure sheaf of x of O. So this is, again, this maybe requires more explanation, but this is really not difficult. Okay, so that's kind of the construction, and so kind of maybe conclusion is this. So conclusions. First of all, we have a construction. When y is t star x and x is smooth F1. What is non-obvious is computation of this y check explicitly. I told you that some examples this can be done. There are many more examples, and there are some examples when it's not done. But somehow in this example, you have to, in each particular example, you have to kind of work to see what you get. Because you have this abstract constructionless ring object, and then I have to kind of compute what it corresponds to on the derived geometric satake, and this is actually somehow in every particular example, this is not obvious. Second is that if y is general but smooth, if y is general but smooth, then similar construction works, but somehow it's a little bit more problematic. So somehow it's clear what you have to do here. So here we're considering g modulus on x of k, and if we only have y, don't have x, then instead of x of k, we only have y of k. But we don't want to consider g modulus on y of k. Instead, we want to consider the modulus over some quantization of y of k. And so quantization is a slightly tricky notion, how canonical it is. So for example, if y is a vector space, this is a canonical quantization of a symplectic vector space. But other than that, you have to work a little bit there. And also, you know, when you work with quantization, then this notion of anomaly also appears. And again, I don't have time to discuss this, but at least it's clear that somehow what you have to do in general, you have to replace this d modulus on x of k with modulus of some kind of nice quantization of y of k. And so, kind of a really serious problem is when x, even when y or x singular. Because in that case, somehow, so here our basic object that I took, where was this? This was here. Yeah, basic object was the structure sheaf of x of O. It's clear that that's not the right choice when x is singular. When x is singular. When x is singular, it has to be something like the IC sheaf of this x of O. But that's, in this case, things are kind of slightly too infinite dimensional here to talk about IC sheaves. So this is really open. I don't know how to make the definition, but I should say that, just maybe very last thing I'm going to say, that I didn't have time to talk about more examples, but even in this context, or maybe slightly more general context here, there are many examples when the construction is formally applicable when there is an expected answer, but nobody has checked that the expected answer actually is obtained by this construction. So there's like big source of problems for students just to prove that some expected answers are given by this construction. Okay, I think I'll stop here. Yes.
Is that at all related to like Higgs bundles?
Well, it depends. And no, I mean, it will be related to Higgs, like to actual Higgs bundles. Well, first of all, question is what do you mean by Higgs bundles? It's kind of related to Higgs bundles if you consider X to be the adjoint representation of G. But in general, it's, you know, it involves sections of some. Well, by the way, this story, and if you look at this Ben-Svisak story, then they have a local story, which is more or less very much related to what I was talking about. But also have a global story where instead of a formal disk, you have an actual curve. And this I haven't talked about at all. So, and actually, they have like local story and global story separately in the sense that somehow they don't know how to, they don't have I mean, they should have, but for some reason they don't have an actual formalism which deduces the global story from the local story. That which I think that really there should be one. But I'm just saying that in principle there's some similar version of all this when you actually work with an actual curve rather than a formal disk. But to get actual Higgs bundles will only appear when X is something like a joint representation. Or maybe if X is just a representation, then it will be, well, not Higgs bundle. You know, Higgs bundles are sections of some bundle of endomorphisms, maybe twisted by the canonical bundle, and so if you want to endomorphisms, then you really need a joint representation, so something like this.
Okay, look, your Rx is like a family of affine string of fibers if X.
It's kind of like well, it's sort of well, in that particular case, true. In that case, well, you can actually it's a kind of slightly generalized story. So how if we have this Rx, it actually maps to X of K, and so the fibers actually subschemes in the affine Grassmannian, which are kind of like affine Springer fibers. But the point is, in some sense, you can define analog of affine Springer fibers for any affine variety X with a G action. That's what I'm saying. So literally what we have here, if we take as X, we take the adjoint representation of G, then the fibers of this are literally affine Springer fibers. But you can do it, for example, for any other representation, and you'll get some kind of different notion of affine Springer fibers. Okay.
Обсудить планы на будущее.
Ладно, давай завтра.
Да-да, хорошо.